In this webcast, we want to compare the molecular orbitals of a linear pi system 135 hexatriene, which has 6 pi electrons, to a cyclical system, namely benzene, which also has 6 pi electrons. Each of these systems consists of 6 carbon atoms and they're sp2 hybridized. And since they're sp2 hybridized carbon atoms, that means there's 6 p atomic orbitals left over, and those 6 p atomic orbitals can come together to make 6 pi molecular orbitals. Those 6 pi molecular orbitals will be filled to the degree possible with those 6 pi electrons. Let's take a look at the molecular orbital diagram, and you can see that the molecular orbital diagram for benzene has a different arrangement of energy levels than the energy levels of the linear 135 hexatriene system. Those 6 pi molecular orbitals in 135 hexatriene are all ordered consecutively from low to high, but in the case of benzene, the middle 4 have pairs of degenerate orbitals. That is, the levels psi2 and psi3 are the same energy, and the psi4 and psi5 energy levels are also the same, and that's what we mean by degenerate. The calculation that yields these energy levels is something that you don't need to know, but what we would like to do is to analyze the pictures, the molecular orbital pictures, to try to understand in more detail why these molecular orbitals have the structure that they do. Let's start with the hexatriene. You can see that the sign of the p orbitals is the same above and below that nodal plane for psi1. That's almost the case for psi2, but you can see that there's one change of sign as we proceed, and it's right in the middle. We call that a node or a nodal plane, and you can see that for psi3 there actually are 2 changes in sign that take place, and so we see that the energy level of the pi system rises as the number of nodal planes, or nodes, increases. We have 3 nodes in the case of psi4, we have 4 nodes in the case of psi5, and psi6 has a node between every other adjacent p orbital on adjacent carbon atoms. A similar situation arises for benzene, where we have in the bottommost, the most stable molecular orbital, a set of p orbitals that all have the same sign. Then in the next set of molecular orbitals, we have a change in sign that takes place. You can see that across the ring, the p orbitals change sign in going from the left half to the right half. Now in psi3, there are 2 atoms that actually contribute nothing. They contribute none of their p molecular or p atomic orbital to the psi3 pi molecular orbital. And that's why they're represented like that without any p orbital drawn. And there's a nodal plane that separates the front half from the back half, and you can see that there's a change of sign that takes place from those p orbitals. So psi2 and psi3 have 1 nodal plane. Psi4 and psi5 have 2 nodal planes, and you can see how that dissects the molecule. And again, there's psi5 that has 0 contributions of p orbitals on those atoms. Psi6 has 3 nodal planes, one that slices the left half from the right half. You can see the change of sign from the left half and the right half. Another change of sign along this diagonal, and you can see the change of sign that takes place along that nodal plane. And then finally, the other diagonal, you can see that there's a change of sign there as well from the orbitals that are on either side of that nodal plane. So the number of nodal planes is related to the energy of that pi molecular orbital. I think analyzing the nodal planes is more difficult than the concept that I'll illustrate on the next slide. On the next slide, you're going to see the exact same molecular orbitals, but our analysis is going to compare adjacent carbon atoms and determine whether there's a bonding or an anti-bonding interaction. Let's take a look at that. So we have the same set of orbitals here, but let's start over here with the hexatriene molecule. Notice that adjacent atoms have p orbitals of exactly the same sign. Altogether, we have 5 bonding interactions. In psi2, we have 4 bonding interactions, and then we have 1 anti-bonding interaction. And so the number of net bonding interactions that we have is 4 minus 1, or in other words, 3 bonding interactions. In psi 3, the next level up, we have 1, 2, 3 bonding and 1, 2 anti-bonding, or in other words, 1 net bonding interaction. And that's where we draw the line. Those are the filled levels. The empty levels, you can see, have 2 bonding and 3 anti-bonding interaction, so 1 net anti-bonding interaction. You can keep going, up 3 anti-bonding and 5 anti-bonding for the highest level. We can apply that exact same analysis to those molecular orbitals in benzene, and we can see that in the bottom case we have adjacent p orbitals having exactly the same sign, a net of 6 bonding interactions. Above that, the next 2 levels have a net 2 bonding interactions. So in the psi 2 on the left, we have bonding, 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 4 bonding interactions, and then we have 1, 2 anti-bonding interactions, so a net of 2 bonding interactions. In the case of psi 3, where we have those non-contributing those atoms that contribute none of their atomic p orbital to the pi molecular orbital, we have a net 2 bonding interactions, and so that reveals how these are degenerate pi systems. Psi 2 and psi 3 are degenerate. In the next set of orbitals, we have 1, 2, 3, 4 anti-bonding interactions, and we have 2 bonding interactions, and so we have a net 2 anti-bonding interactions. And you can see that psi 5 has only 2 anti-bonding interactions. Both of those are degenerate, with coming in at 2 anti-bonding interactions. Psi 6 has all 6 anti-bonding interactions. Now, if we want to know where the stability of benzene comes relative to cyclohexatriene, just look at how many of the pairs of electrons are in bonding molecular orbitals. So here we have one pair that is in a molecular orbital that has 6 bonding interactions. So that pair of electrons accounts for a stability of 6b, we'll say. Then we have 2 pairs that have 2 bonding interactions, and so we have a total of 4 bonding interactions there. Altogether, the benzene would have an energy associated with it of 10 bonding interactions. If we look at the 1,3,5 hexatriene molecule, we have 1 by 5 bonding, we have 1 by 3, and we have 1 by 1. So we have a total, in the case of 1,3,5 hexatriene, of 9 bonding interactions. So the energy of 1,3,5 hexatriene has pairs of electrons that contribute energy of 9 bonding interactions, whereas the case of benzene, we would have pairs of electrons that are in molecular orbitals that contribute an energy of 10 bonding interactions. And that has to do with the cyclical versus the linear nature of these systems, and it's that difference which accounts for the special stability of benzene.